LaHoy's.
Yeah, the usual one.
Usual. Assuming that to the right is positive, then the total initial momentum is 2. I can still get away with Descartes since that's written there. My total final momentum.
Two Descartes.
What is the momentum of this? So the P3 final. What is the final momentum of the 3 kilogram mass?
-6.
Go ahead and finish
The
it off.
unit with the D.
For those who are not understanding my deep southern accent here. I can't remember if there's an S at the end or not, but the unit Descartes.
There is an S.
There is an S. Okay.
I think that, like, 75 is more.
I think therefore I am guy.
Yeah,
The person who's
Yeah, it's
on
an
Earth
S.
with Cartesian plane.
yeah.
There's an S.
There is an S.
Okay. I did not capitalize it because of the name of the unit, not actually. All right, so I know my total is 2. This is -6, so what does this need to be? What does this momentum need to be so that my total is 2, given that that's -6? So D2 final.
8. D.
So if we take the -6D plus the 8D, we get D2D. And so that's got to be equal to 2 times V2 final. And so V2 final has to be 4 meters per second. Oh, sorry, I scrolled that for you. If I presented it like I did it over here, this is what it would look like. That still stays the same. Then this becomes 3 times -2 plus 2 times V. So I get 2 is equal to -6 plus 2V. 6 plus 6. 8 is equal to 2V. V equals 4. That's the math part. Questions here?
So it does still go to the right, but then why? Wait, mass 3 would still technically go. You said it collides into 1, right?
The 3 kilogram hits the 2 kilogram and the 3 kilogram bounces off.
Oh, yeah. I thought you said that they both go that way.
Not in this problem. Let's find out if this is realistic. Is this possible? Well, momentum is conserved, so we're good on that. Matter of fact, whenever you see a collision problem, I would like you to immediately think conservation of momentum. So it's a collision problem. We thought conservation of momentum, it's also the chapter. But how can we know if this is even realistic? Well, now we have to bring energy into it. More specifically, the kinetic energy. Let's figure out what our total kinetic energy is. You know I'm about to ask that question. If all of you are prepared. In unison, chorus of angels. Here we go. Let's dazzle the international audience. What's the formula for kinetic energy?
1/2 mv squared.
There's a little bit of a musical tone there. All right, so I've got 1/2 mv squared. So for this one, it's 1/2 times 3 times 4 squared, which is 24. This is 1/2 times 2 times 5 squared, which is 12.5. So what is my initial kinetic energy? Total.
$49
Let's throw some units into that.
joules.
Alright. So my total initial momentum is, sorry, wrong word. My total initial kinetic energy is 49 joules. Let's figure out what it is afterwards. So over here, I've got 1/2 times 3 times 2 squared.
Do you not have to subtract it or anything? Or do you just add it up? I thought,
You just add up, they're scalars. So even if you, this is technically speed squared. So the negative sign is an indication of direction, and this doesn't have direction in it. But even if you put a -5 here, you're squaring it, so the negative would go away.
This might be dumb, but where's the 49 from?
24 plus 25.
Do you see where that is 24 joules of energy,
No.
of kinetic energy? Plug it into the formula.
Oh.
You get 1/2 times 3 times 4 squared, which is 24.
Mm-hmm.
Okay. 1/2, 2 times 5 squared gets you 25, and then the total add. Yeah, it seemed like you realized that before I got there, but sorry about that.
I blinked out at the worst time.
Other questions? So I know that let's look at the total kinetic energy afterwards. For this one right here, it's 1/2 mv squared, so m is 3, v is 2, and doing the fancy math, this is 6 joules. Over here, we get 1/2 times 2 times 4 squared, which is 16 joules. So K final, what is my total final kinetic energy? Not a trick question.
Uh, 22 joules.
What'd you say?
22 joules.
Yes. And how'd you get that?
I just added 16 and 6.
Yeah. It's just kinetic energy of that, it's the kinetic energy of that. So we lost energy. They didn't stick together, but we lost energy. This is what I refer to as an imperfect collision. So let's take a look at some vocab. And the different types of collisions. So in all these collisions, momentum is going to be conserved. So the type of collision depends upon what happens with the kinetic energy. So if the kinetic energy initial is equal to the kinetic energy final, there are two traditional naming conventions, and then I've created a third one. So naming convention number 1, this is a perfectly elastic collision. Under naming convention number 2, this is an elastic collision. Now, if the initial kinetic energy is bigger than the final kinetic energy, and they do not stick, under naming convention number 1, this is called an elastic collision. And this is called an inelastic collision. if the initial kinetic energy is greater than the final kinetic energy, and they do stick together. Under naming convention number 1, this is called an inelastic collision. And under number 2, this is called a perfectly inelastic collision. You can see where potential confusion would come up. In order to sort of eliminate confusion in my head, and hopefully students' heads, each book might do it a little bit differently, and it's just one of those things that I can't remember which book does which. So I said, well, let's just take the ones that are not potentially confusing, because I got elastic and inelastic, 2 different places there. So I call this perfectly elastic collision. And this one I call a perfectly inelastic collision. Now in the middle, I didn't really have a name for it other than it wasn't either of those, and then a student suggested imperfect, and I liked it. So this is imperfect. You just stand up and do jumping jacks or something. You're struggling.
We could have died in the other.
Great ring tone. Now, there's another category. If you gain energy, gain kinetic energy in the collision, and there's no explosion or something else that would add it into it. So if initial kinetic energy is greater than, is less than the final kinetic energy, in the absence of no explosions, no additional source of energy. This is what both of these will call impossible. I call it Flubberesque. However, if you did call it impossible, then I would accept it. You're not going to create energy, and assume some of you have seen The Absent-Minded Professor or Flubber. I got one of you has seen.
It's been a long time, but I have seen it.
You watch The Absent-Minded Professor, one of those versions, or Flubber?
I think floated.
Oh, okay. Flubber is a substance that if I took it and I bounced it, it would bounce higher than it started with. So it somehow gains kinetic energy when it hits an object.
Is that possible?
Well, no. There are statistical fluctuations where it might happen, but odds are way against it. To the point of
Like the top physicist with the materials, is it?
no. It would be a quantum fluctuation where suddenly energy gets gained. There's a non-zero probability, but it is so incredibly small that
It's never gonna happen.
it's not going to happen. And even if it did happen, odds are you're not going to notice it before it corrects itself in a sense.
A trampoline with like somebody like doing flips and then like 5 people around them increasing its height.
Yeah, but the energy's coming from the people.
He's saying if it just gets added out of nowhere.
If I took a crane, lifted you over a trampoline and dropped you, and you just stayed stiff-legged, so you're not springing or anything like that, you're not adding any energy into the system, then you will not bounce off as high as you did before. And potentially will break your legs. All right, so there's the vocab over there. So, and then perfectly, so that's why I call this an imperfect collision. We lost kinetic energy. All right. Now for the potential contradiction. I have a mass. What is its velocity?
0.
If I drop it as it's falling, is the velocity still 0?
No.
But if the velocity was 0, what was its momentum? If velocity is 0, what is the momentum?
0.
Okay. As it fell, was the momentum 0?
No.
So it seems like it gained momentum. And I've just gone through this bit about conservation of momentum. Why did that gain momentum when I talked about momentum is conserved? What happened to it?
Acceleration of gravity? Or weight?
Okay, but there are forces involved in the collisions also. You're almost there.
It had
Potential?
potential energy, yeah. That one.
Well, those might have potential energy also. Momentum, when I did the conservation of momentum, I didn't even bring height into it. Height was not a factor. All right, so let's take a look at the two differences here between this and that. Why did it fall when I let go?
Wait,
Caused by what?
am I allowed to say gravity?
No, looking for an object.
So,
They're bigger.
It was,
Due to
Earth.
the
There had, yeah, that's what I was going for. Forces require two objects and some type of force. So I had the two objects is that mass and the Earth, and then the force was, there was gravitational force between them. Weight in this particular case with the small mass. When we looked at the momentum in that case, in the case where I dropped it, all I concentrated on was just the mass that fell. I didn't care about the Earth. So if I'm looking at just that mass that's falling, but it's being influenced by something else that I'm not looking at or considering, that is known as an open system. Whereas in this case right here, I was considering both masses. There's no other influence. There's no forces acting on either of these masses from anything else. It is only just those two masses. That is a closed system. So in a closed system, momentum is conserved. That's supposed to be a D. In an open system, well, momentum will change based upon the impulse. Now we can show that over here. Let me get rid of some of this stuff. Let's see, let's get rid of the yellow. All right. Instead of looking at the whole system where momentum is conserved, let's take a look at just the 3 kilogram mass. The momentum of the 3 kilogram mass, P3 initial, was 12 Descartes. P3 final is -6 Descartes. So momentum definitely changes for the 3 kilogram mass. So if I'm looking at just the 3 kilogram mass, momentum, it's an open system because it's influenced by something else. What is the impulse imparted to the 3 kilogram mass? That's the same question as what is the change of momentum of the 3 kilogram mass?
-18.
Yeah. So the impulse, what letter do I use? might use a J sometimes and I sometimes. A J with a vector symbol over it is equal to negative 18. Negative 6 minus 12. Now let's take a look at the 2 kilogram mass. P2 initial is negative 10 Descartes. So I go from negative 10 to 8. What is the impulse imparted to the 2 kilogram mass?
Positive 18.
So if I look at each separately, open systems, loses potential, or loses momentum, this gains momentum. If I look at it combined, well, the total is 0, because momentum was conserved. Questions up to here? Now I'm gonna guess what you're thinking right now. You're going, hey, this stuff is great, but is there any way we can have a system of equations where we have to solve for an unknown? Did I nail that? Okay, and if everyone except Dominic was probably thinking it then. Well, the answer is yes. Yes, we can. Because what we're gonna do right now is solve the perfectly elastic collision. And we'll start out with the same thing. So I have the 3 kilogram mass heading to the right at 4 meters per second. I have the 2 kilogram mass heading to the left at 5 meters per second. If it's perfectly elastic, well, if it's a collision, momentum is conserved because I don't have any outside influences. It's a universe with just these two things.